Right, let's now consider the next question on this worksheet of ours. They say here, okay, ammonia is known to form a common ion when dissolved in water. Discuss the formation of this ion with reference to the bond type and show the acid-base reaction in the formation of the ion. Okay, so obviously they're talking about ammonium, ammonia, right? So let's have a look. We know what happens. Okay, what have we got? We've basically got a situation where, just move this out the way over here. Okay, we've got NH3 plus water. Okay, now what happens to this? Well, very often you can actually intuitively work it out if you're not 100% sure. Because you know that NH3, the only other thing you know about it is it does NH4 as well, doesn't it? So let's take a guess and say, oh, come on. Let's put it to NH4, and we know that's a +1, isn't it? So what has actually happened? We also know that water can dissociate into NH3 plus H plus OH minus going to NH4, right? Now, what has happened here? Remember, an acid is a what? Acid is a, let's just put it down here. Acid is a proton donor. And once again, if you get stuck and not sure in a test or an exam, just think, you know the basic acid. The basic acid, HCl, hydrochloric acid, in our tummies, it's a part of the processes we use all around us. Hydrochloric acid, HCl, you know that dissociates to be an H plus a Cl minus. Therefore, there's the proton. Okay, coming from the acid is an H. H is a +1, isn't it? Okay, so we've got NH4 and plus there, and we've got our OH minus that it goes down to. All right. So, what happened here then? Well, we said, all right, the one that donated the proton was the acid, which means that the water must have been our acid, correct? Okay. Therefore, we know, okay, interesting, base, right? And we know the one that got it, okay, and we say we've got the water donated the acid, and over here we've got our base. Okay? Because it received the proton, didn't it? Okay? So if it received the proton, this NH4 has now got a proton in excess, which means it can donate it, which means this is the acid-base pair, and the acid, and you know, once again, OH is a base, isn't it? The hydroxyl is a base. We know that. Okay? So there's our conjugate pairs over there. Like so. Okay? It's actually very logical to work it out if you think about it. You only have to find the one that's giving off, or look for an OH that's sitting in there. That's your base, and you can work backwards, okay, to find where they come from. Of course, water, you know, can act both ways, can't it? Therefore, it's an amphilide. Same with H2SO4, diprotic acid. As it goes through the dissociation, remember, H2SO4 can dissociate to H plus HSO4 minus. Then the next level is H plus again, plus SO4 minus 2. Remember the valency of the polyatomic ion sulfate, minus 2. Therefore, this here at this point, right, this character here, the HSO4, okay, can still donate, so it can be an acid, but it can also accept a proton, can't it? And it can be a base. Because if I add that back, it goes back to H2SO4. So it's the amphilide, it's going both ways. Okay, right. So there we've looked at that. Now let's have a look at they've asked us, what is this NH4 and what is the type of bonding, etc., that happens? let's go and answer that part of the question. What we've got for that part of the question is this one, isn't it? We've got this. We've got the NH4 is forming. Now let's have a look how it forms. Right. What happens is we had NH3, right? So let's have a look. Remember we had our lone pairs up there. And we had our hydrogens linked in here, correct? We've just done this one. That lone pair over there. What we have to ask ourselves is this proton over here. Okay, let's have a look for him. Let's make him blue. This proton, this H plus, is now on its own. Well, not that one. It's actually the one that comes from the ammonia up here. This one. Okay, it's this proton here coming down. Right? The proton that came from the water. Where does it go? Well, essentially the proton on its own is unstable. It links up with something. It doesn't hang around as an H plus ion. So what it does is it looks for some companion of another, and it isn't going to find any easily. So what it does is it goes and it says, hang on, look over here. I'm a positive. I will be attracted to this electron pair, won't I? So essentially this H plus comes and sits over here, right? It's attracted to those lone pairs up there. Now you can see what have we got. Okay, we have got NH4, but we've got a proton extra, so it's a plus, right? If you did the electron configuration, you'll see that here we've got 1, 2, 3, 4, 5, 6, 7, 8, but we've got an extra proton that's come in. So we are an H plus. Okay, so we have now become an H plus ion. Now, so okay, well, what do we call that type of bond? It's got a special name, and it is called dative covalent, or also called coordinate. Okay, it's called a dative covalent or a coordinate bond, right? That is what is happened. Okay. Okay. Now let's move along to the next section. Okay. The acid reaction we've done, the bond type. Okay. We've got that one. Okay. So now we can say, okay, show what happens if ammonium is added to a carbonate. Okay. Right. Let's have a look what we've got. Okay, let's add to a carbonate. We know that we've got over here NH4 plus. Yep. We've got NH4 plus a carbonate. Okay, CO3 minus 2. Right. What is happening here? Because essentially we're looking at the acid-base formation here, aren't we? We are putting carbonate and ammonia together, ammonium. Right, what happens here essentially is this. You form NH3 plus HCO3 minus. Okay, the CO3 goes that way, this one goes that way, right? And what we do is we say, right, this proton from the NH4 has gone. Okay, so essentially this was the donor of it, so it was the acid, and this is then the base form. Okay, therefore this HCO3 must be the acid form up here, and this must be the base. Okay, those of you who've done the whole series throughout the grade, you'll have seen we've done 4 or 5 specific ones. It's just worth remembering those 4 or 5. And this is one of them that comes out as, let's say, a standard form where they ask you the acid-base reaction. Always remember, if you've got an acid and a base reaction, you've got an acid plus a base reaction going to your base plus your acid reaction on that side. You've got to find out which one is which. And you look for either an OH or you look for which one has donated a proton. Okay? That's pretty straightforward. Right, now, let's move along to the the next in this section, put you out the way now. Okay. Let's have a look at the next one. The next question involves the calculation of the pH. Okay. Now remember that in the theory, the pH, okay, was the scale obviously, and to 14. Okay. Okay. Let's just have a look here. What was 7? 7 was neutral, correct? Okay. This side here, acid. Okay. This side was alkaline. This is our base right over here. So up here you'd find your NaOHs. Down here you'll find your HCl's, etc. Correct. But the definition of the pH was the following, wasn't it? pH is equal to negative log of the concentration of hydrogen ions. But we do it as H3O plus, correct? Now let's just have a look. Where did we get this 14 from? Right? And let's have a look what, because you saw I rubbed it out. What would the lowest base be? We know the 14. What would this guy be here? Well, it's going to be the form that we can get that into the lowest number, isn't it? Right? Okay. So let's have a look. pH. Can we have a pH of 0? Right? If we have a pH of 0, right? Then we say 0 equals negative log of H3O plus, and then we'd use our calculator and we would put, okay, that up, okay, okay, well, minus 0 is going to disappear, so it's going to go up to, my calculator's not, okay, shift, okay, of, oops, okay, shift 10 to the x of 0, 1 equal to that, right? So now, let's have a look what actually happens. Hold on to that thought. Let's just have a look what happens over here. What happens with water? Water dissociates, right? We've got H2O plus H2O, and what do we get? We essentially get the H3O, right? Plus, and we get OH minus coming in, don't we? All right? Now, we know that at any point, the concentrations of those of water, all right, the dissociation constant of water is 1 times 10 to the minus 14, right? That's a given. Now we've got to say to ourselves, let me just see if I have done this example for you. Pretty sure I have. Yeah. Okay, 1 times 10 to the minus 14. What is happening here? We know that at this point, right, there you can see the 14 is coming in, can't you? So the water dissociates and we get that. So we're saying that when those are equal there, right, we have got pH, okay, equal to negative log, okay, of, let's have a look at negative log of 1 times 10 to the minus 14. Okay, let's have a look at that just for interest. What does that give? Okay, negative log 1 10 to the minus 14 is going to be equal to, it gives us 14. Okay, so therefore if the entire concentration was OH, it would be 14, wouldn't it? Okay, what if we say to ourselves, all right, sorry, it would be H3O, right? Let us now say, all right, obviously those are going to be equal, right? So therefore, divided by 2, which means that and that are balanced, so we're going to get 7. So what we're saying is that the negative log, okay, of that divided by 2, because our concentrations are going to be the same. Remember, when the water dissociates, the concentration of these two remains the same. Okay? Let's look at an example of it, all right? And then we'll go back and finalize the thing over there. Okay. They say here, 30 grams of NaOH is dissolved in 250 milliliters to prepare the titrant. Okay? Whoops, sorry, my bad. 2.1. Calculate the pH of the following. All right? Let's have a look at the pH of this. All right? The pH of this one here is 0.2 HNO3 and H2O. Right. So what do we say? We say HNO3 is what? Nitric acid, right? HNO3 plus H2O, right, which is our water. And what are we going to do? That is going to go to H3O, because this here is going to donate the proton, right? It's going to dissociate to H plus NO3 minus, right? There, and we're going to get plus and NO3 minus over there like that. Let's once again have a look at our recipe. It's 1, 1 gives us 1 and 1, correct? So, therefore, now let's have a look. What are we given? We are given, and they say 0.2 grams of that, right? Is into the titrant, or rather, no, it's just in 200 centimeters cubed H2O. And we say, right, in our volume, okay, the volume is 200 centimeters cubed, right? So let's put in here, volume 200 centimeters cubed. Straight away, we've got to put that to decimeters cubed, 0.2 decimeters cubed, because you're going to divide it by 1,000 to get it to there, right? Okay, so now we know that. So, right. Now, you know that this is a strong acid. Nitric acid, remember, you've got HCl, HNO3, and H2SO4 are the strong acids, right? So what is happening is that in the strong acids, they all dissociate straight away. So we get a full dissociation, okay? Not a part, it just goes to H plus and NO3 minus. The H plus hangs onto the water molecule to give us an H3O plus. Therefore, we say, right, what actually happened here now? Let's look at the number of moles, because we know we've got to get to number of moles. Number of moles, first we need molecular mass. Can you see how important that table is? Okay, molecular mass, and in this case is 63 grams per 1 mole. Okay, so therefore we've got here 3.175 times 10 to the minus 3 grams. Okay, sorry, my bad, moles. My mind just wandered there. Minus 3 moles, right? How do we do that? Remember, we said 63 is 1. We've got 0.2, therefore how much of that have we got, right? So we've got 3.175 times 10 to the minus 3 moles of that. Apply the recipe now. Remember, we're at moles, we apply the recipe, okay? So if I've got that of that, how much H3O do I get? I get 3.175 times 10 to the minus 3 moles of that. We do this because that could be a 2 or a 3. Remember, if that was H3PO4, that would be a 3. H2SO4, that would be a 2. Okay, so now I say, right, now I've got the concentration of that. So let's have a look and say, yes. Now we say, right, therefore, what is the concentration? Remember, we're looking for the concentration for our formula. So we say the concentration of this is 3.175 times 10 to the minus 3 divided by 0.2, which is going to be equal to 0.01587 moles per cubic decimeter. Therefore, let's go back to the original. Therefore, the pH of that is going to be minus log of that concentration, 0.01587, and it's going to give us 1.82. Okay, that's the pH of that. So you see what we did? We set up the balance reaction, put what we were given, molecular mass, because we need to get a number of moles, because we've got to put it into our process of to find the concentration It's the number of moles divided by the volume. Remember, concentration, let me just go back up here. There we go. Concentration is equal to N over V. Remember that bit? Okay, now let's have a look at the one where they're asking us, if you have a look there, they say, right, what is the pH of 0.3 grams of KOH in 200 centimeters cubed of water? So let's just write down our chemical reaction first. They've said KOH plus, and I'm just putting the water in brackets there, and we know that it's a strong base, therefore we get a dissociation like that, right? In this case, I don't need a proton acceptor, so the water doesn't have to come into the equation, right? So let's put down let's put down first of all our recipe, shall we? Red 1 1 1 1. We can ignore the water for the moment. This is our recipe. Let's put down next, okay, what are we given and required to find? Okay, we are given in this case 0.3 grams of that, and let's put down molecular mass, moles, concentration, and we are given a volume over here of 200 centimeters cubed. Convert straight away to 0.2 decimeters cubed, right? So now molecular mass of KOH is going to be equal to 56 grams per mole, like so. Therefore the number of moles is going to be equal to 0.3 divided by 56, 5.357 times 10 to the minus 3 moles. Now we've got N, so what do we do when we've got number of moles? We apply recipe, correct? So therefore we can say that each of those we're going to get 5.357 times 10 to the minus 3 and 5.357 times 10 to the minus 3 moles of that. Now the reason here is we're not working with an acid, we're working with the base. So we know we're still going to be looking for the OH bit, okay? Let's just get the concentration of the OH. So now the concentration is equal to N over V, which is 5.357 times 10 to the minus 3 divided by 0.2, and that gives us a concentration, if my maths is right, of 0.02678 moles per cubic decimeter. Can also write it like that, okay? But this is the concentration of OH, isn't it? Okay, it's not the concentration of the H3O. So what do we do now with this one? We've got a bit of an issue. Let's see how we're going to deal with it. What we're going to do is we're going to say we know that now when we're using a base, you invoke this dissociation constant of water, where we've got H3O plus times OH minus equals 1 times 10 to the minus 14. Remember that one? Look, we've got over here, this is concentration of OH minus, isn't it? So let's put it in. Times that one, 0.0278, okay, 0.2678. Let me just write it neatly. 0.02678 equals 1 times 10 to the minus 14. Okay? Therefore, the concentration of H3O plus is going to be that divided by that, which gives us 3.734 times 10 to the minus 13. Okay? Therefore, the pH is going to be equal to negative log of 3.734 times 10 to the minus 13. And if you put that into a calculator, you're going to get 12.43, which is exactly where you want it. It's pretty high up on the alkaline side, isn't it? Okay. Now, what is all this for? Well, it actually comes down to the fact that we're going to be looking at doing titrations now, aren't we? We're going to be looking at the next one where they talk about a titrant, okay? Now the titrant, okay, is basically what we're going to use to actually do the titration with, isn't it? So we are going to, they say here, okay, 30 grams of NaOH is dissolved in 250 milliliters to prepare the titrant, and this is used with 2.5 milliliters of H2SO4. Okay, 16 milliliters of the titrant is neutralized as the acid. Calculate the concentration of the H2SO4 that is in the equation. Okay, so what I'm going to do is I'm going to do that one in the next section because it's quite a long piece that we're going to have to work through and talk through. So I'd rather cut it now and then continue with that bit in the next bit.